Over the last 20 years, telecommunication networks have taken a quantum leap in bandwidth and data capacity, which has forced the evolution from copper cables to optical fibers. Fiber optics is the only medium capable of keeping pace with today's ever-increasing hunger for more bandwidth. As a result, fiber optic cables have replaced most copper cables in networks covering any significant distances. The dielectric nature of optical fibers provides immunity from crosstalk, electromagnetic interference, and electronic signal degradation, but can also make electronic means of cable identification extremely difficult. But why would someone need to electronically identify a fiber optic cable? As with copper cables, fiber optic cables are not all placed at one time by the same installers. This can lead to errors and omissions in labeling and cable management, especially when crews are under tight deadlines. Over time, labels can become faded or even fall off the cable. In some cases, messy installations meant as temporary emergency restorations become permanent due to bad documentation, staff turnovers, and carelessness. This is even worse in metropolitan area networks, where many service providers may be sharing the same vaults, manholes, and even ducts. The cost of bad cable management quickly becomes apparent when a service provider or contractor must make an express or mid-entry into an existing cable span. If the correct cable isn't properly identified, the technicians may enter another organization's cable and not be aware of the mistake until the fiber identification process is started. At best, the cable would need to be protected by an unplanned splice closure for the cable's operator and users. A worse situation could be an emergency restoration. Which cable must be cut? The technician facing this dilemma may feel a sense of panic, realizing that cutting the wrong cable could result in millions of dollars of lost revenue. In the case of circuits carrying 911 emergency traffic, cutting the wrong cable could easily lead to loss of lives as well. So it is of critical importance to identify the correct cable before work begins. Because optical fibers do not radiate energy, it is impossible to use conventional RF signal detection equipment to locate a purely dielectric fiber optic cable. Even in cases where the cable is armored or contains metallic messengers, national electric codes dictate that these components be bonded to ground at points where metal parts are exposed, making their use as locate conductors impractical. Other conventional techniques of cable identification include the use of an OTDR or fiber identifier. The fiber identifier approach is common, but can only be used once the cable jacket has been removed and the fibers have been accessed. Another technique used is the introduction of microlosses in the target cable by a bending clamp or freezing. Physical cable bending results in a macro bend, while the freeze method introduces a micro bend to the cable's internal fibers, either of which can be seen on the OTDR if conditions are right. However, many fiber optic cable structures are rigid, and all cables contain buffering to protect the fibers from the effects of bending. As a result, slight bends may not be visible to the OTDR, but if bending becomes too severe, the cable may suddenly kink and damage the internal fibers. Fortunately, there is a simple solution in the form of the FIBERPRO Model CI4000 Acoustic Fiber Cable Identifier, or AFSID. Developed for practical field applications and the requirements of large telecom customers, the AFSID uses optical interferometry for cable identification. This technique transforms the cable into an extremely sensitive audio detection device. The patent-pending innovation of the FIBERPRO AFSID system provides a user-friendly, non-invasive way of fiber optic cable identification that does not require cutting, bending, or freezing of the cable. This instrument is an extremely useful outside plant tool that greatly reduces the time and expense of cable management, maintenance, and repair of fiber optic networks. With the AFSID, the user can easily find a target optical cable by gently tapping on it. The AFSID system detects the tapping and provides an audio output as well as a visual display for use in noisy environments. The instrument is terminated to a pair of spare or dark fibers in the target cable, and the fibers connected at the remote end of the cable span with a jumper to form a loopback. Gentle tapping applied to the cable at almost any point along the span can easily be detected by the AFSID as an audible sound as well as a variable LED bar display. The technicians maintain voice contact through the use of cell phones, and to make finding target cables easier and faster, the AFSID is connected to one of the cell phones. This allows the remote technician to hear the output of the instrument while various cables are tested. This amazing instrument makes possible for the first time the ability to identify specific fiber optic cables by simply tapping on them. And its wide dynamic range allows it to detect tapping sounds up to 100 kilometers away. The simple, quick, and non-invasive operation of the FIBERPRO AFSID ensures that poor cable management, faded or missing labels, or undocumented repairs will no longer pose a serious threat to your bottom line. This graphic shows how the AFSID system works. Light from a laser source operating at 1550 nanometers passes through an optical isolator, through an optical mixing and signal management module, to the optical ports on the rear of the instrument. Using optical jumpers, these ports are terminated to a pair of spare fibers in the cable to be located, and a loopback jumper or connector is applied to the fibers at the remote end of the cable span under test. The optical mixing module ensures that light from the laser travels in both directions around the fiber loop, forming an interferometer. Because laser energy is coherent, splitting the laser light into a pair of beams and allowing them to interact over a long fiber span produces a pattern of interference in the fibers. If the light were visible, this interference pattern would show up as a series of brighter and darker regions along the fiber span. The interference pattern also returns to the optical module, where it is monitored by a detector system. However, an optical isolator prevents returning light from entering the laser's optical cavity, which would cause system instability. Under steady state conditions, the interference pattern would not change along the fibers, and the detector would see the same intensity of light over time. However, if the cable is bent, moved, or even tapped with a solid object, microbending slightly changes the optical path length the laser beams are traveling in. This moves the position of the interference pattern in the fibers, so the detector will now see a difference in light intensity that varies with the strength of mechanical perturbation of the cable. In this way, the entire cable span acts as one giant microphone that is extremely sensitive. As an example of the sensitivity of the AFSID system, if a 20-kilometer reel of bare fiber is terminated to the instrument, the reel of fiber can easily pick up people whispering from across the room. This extreme sensitivity to acoustic waves can have a disadvantage when trying to identify a fiber optic cable. Seismic disturbances caused by trains and road traffic can produce a high level of background noise, making it difficult to pick out the tapping signal. In addition, high sensitivity can also allow Crosstalk to produce false positive test results. Because cable jackets are rigid, mechanical disturbances introduced to one cable in a bundle can be coupled to the other cables. For this reason, the AFSID system incorporates advanced signal processing circuitry to drastically reduce noise and crosstalk. Noise reduction is user selectable and provides excellent results as well as greater immunity to crosstalk, but at the expense of reduced sensitivity. The AFSID is also very easy to care for. As with all precision instruments, it should be kept in its rugged shipping case when not in use. Because it is fully automated, it does not require periodic factory maintenance. The most important routine maintenance that you can do is keeping the optical ports clean. This is greatly helped by always cleaning the jumper cables prior to every mating. Contamination from poorly cleaned connector plugs can accumulate in the optical ports over time. The accumulated debris will act as an abrasive each time the connection is mated that will eventually damage the port. It is recommended that the optical ports be cleaned prior to each use with a cleaning swab designed for fiber optic connector ports. Do not use conventional cotton swabs in this application, as they contain oils that will attract airborne contaminants. When not in use, the optical ports must remain capped. The RS-232 port and BNC ports on the rear panel of the instrument are for factory use only and must remain unconnected. For further information on the AusOptic fiber optic cable identifier, please consult the operator's manual or contact FIBERPRO using the contact information on your screen. Using the AusOptic is very simple, but requires a minimum of 2 technicians. One technician sets up and monitors the instrument at a central office location. The other technician travels to the remote location where the cables need to be identified. This is usually in a vault or a manhole. For convenience, a third technician may stay at the remote end of the cable span to connect the loopback jumper or connector to the appropriate fiber ports and move the jumper if required. Alternatively, loopbacks may be placed on selected fibers in all cables to be tested by the field technician before traveling to the site where the locate will be made. The instrument is terminated to a pair of spare fibers in the cable to be identified using 2 FC jumpers. Before making any optical connections, it is important to clean each connector plug to prevent contamination of the patch panel ports or the ports on the AusOptic. If your patch panel uses connectors other than an FC, you will need to use a set of hybrid jumpers. Connect the jumpers from the optical ports on the rear panel of the instrument to the appropriate ports on the patch panel. Connect the headset to the microphone and speaker jacks on the front panel of the instrument. Connect the stereo extension cable to the phone jack on the front panel and then to the headset port of a cellular telephone. Connect the power cord to the rear of the instrument and switch the instrument on. The instrument will initialize and perform a series of self-tests which take approximately 10 seconds. When complete, the low noise and the saturation alarm push buttons will illuminate, indicating the instrument is ready for operation. The field technician accesses the cables to be tested. Be sure to follow all local and national safety codes when working in confined spaces. When the cables have been accessed for testing, the central office technician presses the Set LD Off button to start the instrument's laser. The LED and the push button will flash for a few seconds while the instrument calibrates and initializes the interferometer. During this time, the field technician must not disturb the cables. When the calibration is complete, the Set LD Off button will remain illuminated and the instrument is ready for testing. If it is off, the calibration was not completed properly and the laser must be restarted to acquire a new calibration. Before doing so, check the status of the Loop Open LED. If it is on, this means the loop has not been closed. Check the loopback jumper at the remote end of the cable span as well as the connections to the instrument. Also, be sure you have connected the jumpers to the correct ports on the patch panel at both ends of the cable span. The attenuation of the loop may be too high or the distance may be too great. Keep in mind that the instrument features a wide dynamic range of up to 60 dB, which corresponds to 200 kilometers of fiber at 0.3 dB per kilometer. Because of the loopback, total distance will be limited to about 100 kilometers depending on the actual attenuation of the fiber. However, best results are obtained when the testing occurs between 2 and 20 kilometers from the instrument. The Loop Open indicator also allows you to use the AusOptic as a simple go-no-go cable tester. If the loopback jumper is properly installed, the cable length is within the recommended range, and the Loop Open indicator is lit, it is likely that there is a cable fault somewhere in the span. When the instrument is ready for testing, the central office worker can speak to the field technician through the headset. Both technicians will also hear the output of the AusOptic. The central office technician lightly taps the jumpers terminated to the instrument while adjusting the volume control so that both technicians can hear the signal. The field technician begins gently tapping on the cables in question with a rigid object such as a pen, screwdriver, or pair of pliers. When the appropriate cable is tapped, the signal will easily be heard by both technicians. A visual indication of the tapping sound will be displayed on the LED bar graph on the front panel of the instrument. The optical characteristics of the interferometer dictates that the cable will become less sensitive to mechanical tapping the closer you get to the loopback site. with zero sensitivity at the loopback point itself. When locating cables near the loopback, it is recommended to keep at least 1 kilometer of fiber distance away from the loopback and switch the noise reduction off to maximize sensitivity. In this demonstration, we have a sample of the AusOptic output without noise reduction. Notice the background noise makes it difficult to pick out the tapping sound. When noise reduction is switched on, the background noise is almost completely eliminated, making the tapping sounds easy to recognize. In most situations, weak signals will not be a problem. In fact, the opposite is usually true. If you tap too hard on the cable, the signal can saturate. That is, reach the point where more force does not increase signal intensity. When this occurs, an LED on the front panel of the instrument will flash and a beep will be heard in the headset, indicating that the tapping is too strong. The field technician can then adjust the tapping force as needed. Although saturation does not increase the usable return signal, it does increase the possibility of crosstalk. Strong tapping or pounding on the wrong cable in a bundle can mechanically couple enough vibrations into the test cable to be taken as a false positive result. However, if some simple guidelines are followed, crosstalk is not a major drawback. First, it is necessary to separate cables if they are bundled tightly together. This also makes it easier to access and tap on individual cables. Cable jackets, being made of plastic materials, have a natural dampening effect to mechanical vibrations over a short distance, so unbundling the cables for approximately 1.5 meters should suffice. To reduce the possibility of crosstalk still further, a foam rubber damper can be wound around the test cable at the point where it contacts the other cables in the bundle. In most cases, this will completely eliminate the effects of crosstalk. A package of spiral foam dampers are supplied with the AusOptic. Another innovative method is to use a small MP3 player and a tactile transducer to inject music into the cable jacket under test. The transducers are available from FIBERPRO. Because of its distinct rhythm, music is much easier for a human to detect than simple tapping on the cable, even when there are high levels of noise on the signal. In addition, the higher frequencies of music are greatly attenuated by cable jacket materials. The vibrations of the music pass directly down a very short distance through jacket and buffer materials into the fibers without being carried any significant distance along the cable jacket, so crosstalk is virtually eliminated.